Okay, let's talk about something called the conjugate zeros theorem. Okay, so this isn't very difficult. This is something you'll need to know for the next exam. But let's see what it says. The conjugate zeros theorem. Imaginary zeros of a real polynomial come in conjugate pairs. Okay, have you ever had a conjugate pair? They're delicious. No, that's a bad joke. Anyway, what do I mean by an imaginary zero? An imaginary zero, let's be specific, those are complex numbers with non-zero imaginary parts. Now, I don't just say complex zeros of a real polynomial in conjugate pairs, because remember, every real number is also complex, right? It just has zero imaginary part. So I think this is the best way to express it. Here's a restatement. Suppose that p of x is a real polynomial and p evaluated at z is 0. That makes z a zero of the polynomial p of x, where z is a plus bi, where b, that's the imaginary part here, b is not 0, then its conjugate, remember we had our notation with a bar on top, z conjugate, which would be what, a minus bi, the complex number with a imaginary part, you change the sign on the imaginary part, is also a zero of p of x. That is, p evaluated at z bar equals 0 also. Okay, and let's double check we remember what's a real polynomial. A real polynomial is a polynomial with what? Real coefficients, right? Real coefficients. You need that in a statement of the theorem, otherwise it would not be true. And I'll show you an example of that in a little bit here. Okay, so imaginary zeros of a real polynomial come in conjugate pairs. Okay, so for example, let's do an example here, just an easy one. I just have an imaginary p of x here, so that's a polynomial. It's supposed to be what? Real, is a real polynomial. And suppose that p evaluated at 1 plus I is equal to 0. That would mean what? 1 plus I is a 0 of p of x. Then what could you say? Well, you could say then that the conjugate of 1 plus I, which is 1 minus I, is also a 0 of p of x. What would that mean? That the polynomial p evaluated at 1 minus I must also be 0. Okay? You could have just stopped and said 1 minus I is also a 0 of p of x. Okay? All right. Now, let's look at some questions of a type that will be on the exam when it comes. Here's a question. Find a real polynomial of smallest degree that has 1 and 1 plus I among its zeros. Okay? Well, we're going to think of this. We'll give this a name. We'll call it f of x, say. Okay? I'll leave a little gap here after the equal sign. I'm going to show you why here in a second. But I want to find, first of all, a polynomial who has 1 as a 0. How about x minus 1? If I said x minus 1 equal to 0, then what? 1 would be a 0 of that polynomial. Now, I'm just going to make that a particular factor of the polynomial I'm looking for, right? But so far, I've got this covered. Now, suppose I have this, x minus 1 plus I. Okay? Now, if I was to take this polynomial the way it's sitting and set that equal to 0, you know how to solve this. I would take what? Take each factor, set it to 0, and solve. You see, I would get 1 for a 0 from this factor, and I would get what? 1 plus I as a 0 from this factor. Okay? Now, am I done then? I just have to multiply these two together? The answer is no. Why? The answer why is the following. Notice that I said what? It has to be a real polynomial. Now, from the conjugate zeros theorem, if my answer f of x is going to be a real polynomial, if 1 plus I is a 0, its conjugate 1 minus I must also be a 0. That means I must have this factor x minus 1 minus I in there also. Okay? Now, you can see that these are what? Do you remember multiplying forms like this earlier in the chapter? Remember how I asked you to do that? I have a video on that, multiplying things like this together, and this is why. Okay? Before I say that, and actually multiply these together, let's say I had stopped right there. Let me also mention this, see, just for emphasis. If I had just left these two factors here and multiplied these two out, do you see I would not get a real polynomial in the end? I would end up having a polynomial of second degree with coefficients that are what? Some of them are imaginary. All right. In fact, all of them except the first one would be imaginary. Okay? It would not be a real polynomial. But I claim if I include this factor in there, when I multiply these out, I'm going to end up with a real polynomial. It'll have degree x times x times x. That's x cubed, so its degree will be 3. Now, before I actually do this, there's one other little thing I would like to say here. I said find a real polynomial. Okay, I'm not claiming this polynomial is unique. It almost is, though, because if I take a leading coefficient here, a sub n, where a sub n, or I'll just say a is any what? Any real number, then I would do what? I could multiply this out. I would still have a polynomial that satisfies the condition above, and it would still have what? Degree 3. Okay? So it would still be of smallest degree here. But I see no reason for actually doing that. I'm just saying we could do that in theory here. I'm not going to bother. This way we'll end up with a monic polynomial for our answer, which is often a nice thing to do. Now, when you're multiplying these out, I want you to actually multiply these out to get an answer. Okay? Multiply these conjugate pairs together first. Okay? Remember how we were practicing that? X times x is x squared. And then I get a what? A minus 1x and a minus 1x here when I FOIL, right? That gives me minus 2x. I can ignore the i's when I'm computing the cross term because they have what? Opposite signs there. This is a minus I ultimately, and that's a plus I ultimately. Okay? When those multiply on x, they cancel out. Okay? The next part is going to be plus. Do you remember how it goes? A squared plus b squared. So that's going to be 1 squared plus 1 squared. Okay? No negatives, no i's will appear in that. Okay? No negatives, no i's. Okay? We practiced multiplying a complex number by its conjugate before, and we had that shortcut. A plus bi times a minus bi is a squared plus b squared. No negatives, no i's in the end. Okay? So that's actually x minus 1 times x squared minus 2x plus 2. Let's go ahead and multiply that out. Okay, let's go x cubed minus 2x squared plus 2x, multiplying with the x. And then with the minus 1, I'll go minus x squared plus 2x, it looks like, minus 2. And combining like terms, we have x cubed minus 3x squared plus 4x minus 2, and I'll say that's my f of x, and I'll box in my final answer like usual. Okay? Like I said, on any non-zero, a real constant multiple of this would also work here, but I like this answer. So there it is. Okay? Alrighty, let's work a few more problems along these lines. Okay? Let's have another question. I guess I could have numbered my examples, but I didn't. But anyway, find a real polynomial. Again, okay, I've got that stipulation. A real polynomial of smallest degree that has I and 2 minus I among its zeros. Okay, so I'll give a name like p of x this time to it, whatever you want to call it. Okay, now since it's a real polynomial, I have what? That's imaginary, right? Okay, all right. So that means x minus I is going to be a factor. What else? X minus, what's its conjugate? Its conjugate is negative I. So I've actually got to have what? Negative I. Oh, by the way, this is imaginary, so this is what? 2 plus I. Those have also got to be zeros of this polynomial. So it's x minus negative I, which is really x plus I. Okay? Do you see I get the I out of there when I set that to 0? The negative I out of there when I set that to 0. X minus the entire quantity, 2 minus I. Notice my use of parentheses in there. And then what? X minus its conjugate partner here. Okay? Do you see? I'm setting each of those factors equal to 0. I get what? 2 minus I and 2 plus I respectively. Okay, there's my polynomials. Now I'm going to multiply these together. This is going to be pretty easy. Now you want to group these in the proper way, right? Multiply these together first and these together first. You could multiply just from left to right, but it's going to get ugly if you do it that way. The neatest way to do this is in the order I've just got written there, okay? Multiplying these two together, I've got what? X squared, okay? When I multiply here, I got minus ix plus ix. Those will cause a cancellation. Minus I squared is -1. So that's really what? X squared plus 1. How about these ones? I get x squared, and then I would get what? Minus 2x, right? And another minus 2x. The I parts cancel out. So that's minus 4x. And it's always going to be plus. Okay, what's my a? My a is 2. Okay, so that's 2 squared plus what? No negatives, no i's. My b is 1, so that's 1 squared. Okay, so that's going to be 2 squared plus 1 squared. That's actually going to be 5. So I got x squared plus 1 times x squared minus 4x plus 5. Okay, let's multiply this out. We would get what? X to the 4th minus 4x cubed plus 5x squared. Okay, then when I multiply with the 1, I would get what? Another x squared, and then minus 4x plus 5. Okay, my stacking method didn't particularly make this helpful in this particular case. Don't forget there's a 1 in front of the x squared, so that gives 6x squared minus 4x plus 5. Let's call that p of x here, and let's box in our final answer. So what's the minimal degree under this condition? It would have to be a minimal degree is 4, right? Again, any non-zero real multiple of this would work. But this guy has what? It has zeros I, negative I, 2 minus I, 2 plus I. Okay, so it's got those extra 2 imaginary zeros. Okay, let's look at another one. Find a polynomial of smallest degree that has 2 and I among its zeros. Okay, let's call this g of x for a change. Okay, how about what? X minus 2, and then what? X minus I. Those factors would guarantee what? 2 and I among its zeros, right? Now, what do I have to have here? Do I have to have x plus I as another factor? Oh, wait, no. Be careful here. Do you guys notice that I said find a polynomial? I didn't say it was a real polynomial necessarily, right? So you got to pay attention. Be careful, okay? No, I did not say that. I didn't say it had to be a real polynomial, okay? Let's go ahead and say this. X times x is x squared minus ix, okay? And then what? Minus 2x, okay? And then what? Plus 2i. Now you can actually, what? These are like terms here, right? So maybe you would want to rewrite that. This is the way I would want you to do it. Let's maybe write it this way. Minus 2 plus I, x plus 2i. And we were calling that g of x, so we'll box that in there, okay? Okay. If you included the factor x plus I in here, you would have ended up with a real polynomial. It wouldn't have satisfied the conditions of my question, though, because all I said was find a polynomial of smallest degree. Oops, that polynomial would have had degree 3 also, right? Whereas this one has a degree 2. I never said it had to be real, okay? If I said find a real polynomial of smallest degree, you would have been right. We would have had to include that other term, and we would have ended up with a third degree polynomial. Okay, so don't be fooled. Okay, be careful. Now, here's a slightly different type of question here. Find an integer polynomial of smallest degree that has, sorry, I left has out, that has -1 and 3 minus I among its zeros. Okay, I'll call this h of x. Okay, x minus a half minus negative a half. Okay, all right. X minus negative a half would make x plus a half. Okay, how about this? X minus 3 minus I. I would also have to include x minus 3 plus I there, because an integer polynomial is also a real polynomial, right? So whatever this polynomial h of x is, if 3 minus I is a 0, 3 plus I must also be a 0, right? They still come in conjugate pairs because an integer polynomial is also a real polynomial. Now, if I multiply this all out here, I would not end up with an integer polynomial. Why? Because of that half sitting there. Okay? Because of that half sitting there. When I multiply this out, I'm going to end up with some rational numbers that are not integers for my coefficients here. How can I cure this problem? Well, you notice I left a little gap here. You guys see what I can do? Wait a minute. What if I multiply by 2 here? If I multiply by 2 here, this would be 2x plus 1. 2x plus 1. That's an integer polynomial, right? That's an integer factor. Okay? Well, a polynomial with integer coefficients I'll call as an integer polynomial factor, or an integer factor for short, unless otherwise notified here. Okay, what if I multiply these two together? What would I get here? X squared, I would get minus 3x twice, so that would be minus 6x, because the i's would drop out. And then I would get, remember, plus, what's my a? 3, and my b, 1. So that's 3 squared plus 1 squared. No negatives, no i's. So that would be 2x plus 1. If I set that to 0, I would get the minus a half, right? And this, if I set this to 0, I would get the 3 plus or minus I. Of course, I'm not actually going to be doing that. That's the opposite of what I do. Okay, multiply these. These are what? This is what? 2x cubed minus 12x squared plus, oops, I almost wrote 10x. It's 20x, okay? Plus x squared. Okay, so I've got 1x squared there. You can include the 1 there if you want to on a problem like this, if it helps you avoid the error of not seeing a coefficient and then accidentally turning that into a 0. Okay, that does happen with some students there. So you want to be careful here. Okay, let's make our final statement. H of x is 2x cubed minus 11x squared. What would that be? Plus 14x plus 10. So there, this is the smallest integer polynomial, right? All the coefficients are integers, okay? Smallest integer polynomial that has these numbers among its zeros, okay? Amongst its zeros, if you wish. Alrighty? All right. Now, let me throw in one quick thing here on this problem here. Okay, the last one. Find a real polynomial of smallest degree. Okay, real polynomial, so pay attention to that. Of smallest degree that has -1 as a 0 with multiplicity 2. Well, I would go like this. X minus -1. So that would give me the x plus 1. If I set that to 0, I get -1 as a 0. I want its multiplicity to be 2, right? So that means I would have to have x plus 1 as a factor twice. And then I want 3 as a simple 0. What is a simple 0? Oh, yes, that means it has multiplicity 1. So I would go x minus that 0. So that's x minus 3. Okay, what do we usually do? We would write this instead. We would go like this if you wanted to emphasize powers all the way through. That -1 is a 0 of multiplicity 2. 3 is a 0 of multiplicity 1. That makes it a simple 0. I don't really need that on there, but I just threw it in there for the sake of completeness. Can you square x plus 1 in your head quickly? Okay. Let's go ahead and do this, and we would get what? X, I think I'll multiply it like here, this way. X cubed plus 2x squared plus x. Okay, then multiplying with the -3. X squared minus 6x minus 3. Every term here multiplies on every term there. That's all that's required. X cubed minus x squared minus 5x minus 3. Okay. P of x. Okay. So this has what? -1 with multiplicity 2 and 3 with multiplicity 1, or a simple 0. Okay? Among its zeros. Okay? Now, I might mention in this, if I started doing this, you know, well, let's maybe don't do this. Well, let's just consider if I had that polynomial, I'd have -1 to the multiplicity 7. That would violate this condition, right? So that wouldn't work there, okay? But if I did this, okay, first power, you can drop the first power if you want, but I'd have -1 with multiplicity 2, 3 of multiplicity 1, perfect. If I threw this factor in here, x plus 4, I would also have what? -4 as a 0, right? -4 as a 0. That would not violate the condition that what? -1 occurs as a 0 with multiplicity 2, and 3 occurs as a simple 0. But what would it violate? It would violate that I want what? The polynomial to be of smallest degree. Now, I might have mentioned that on previous problems here. Okay, this is why I do not want this factor in here. You can see this would punch up what? The power or the degree of the polynomial, the highest degree term to the 4th degree. That would violate minimal degree. Okay? Okay, so you should be aware of problems like that, and that those are going to be on the exam that comes up. Okay? Now we're going to talk about some related problems still using this conjugate theorem on conjugate zeros. Okay?